So last time we saw that Galileo had a complicated view of the world, and Aristotle had a much more. Aristotle had a complicated view of the world because he took friction into account, and he kept trying to imagine why things were the way they were. And then later on, well, it started off with Copernicus looking at the heavens, said, "No, life's a lot simpler than this. Just put the sun at the middle of everything, and everything's going to be fine." Unfortunately, it didn't work so well. His math wasn't so good. And so people said, this is a simple idea, it don't work. But it is the right idea, it just needed refinement. And then along came Galileo. And Galileo was, in a way, the father of experimentation, and basically was able to take friction away and look at the way things behave and infer things that weren't obvious. He did experiments and he drew conclusions, and he did not try to imagine why things are the way they are. He just said, this is the way they are. And so one of the things he realized was that when you drop, not a feather and a coin because the feather's got so much air resistance, but if you drop an orange and a cannonball, they'll land together even though they've got different weights. Whereas Aristotle had said that wasn't the case. And then he did some more sophisticated things where he looked at balls rolling down gutters, and he said when you roll down a gutter you speed up, and when you go up a gutter you slow down. So if you roll along a gutter, you're not speeding up because you're not going downwards, and you're not slowing down because you're not going upwards, so you must stay at the same speed, which is just like very analytical. And the conclusion is frightening. The conclusion says that you'll travel at the same speed forever in a straight line, and nothing on earth behaves like that. But he had faith in his analysis. And so now we say the natural state for an object is to stay at rest, which is obvious because if you leave it, it stays at rest, and to travel, or to travel in a straight line at a constant speed forever, no matter what that speed is. And that's just like unbelievable, but it's true. In interstellar space, if you throw something, it will keep moving in a straight line forever. You've got to do something to slow it down. You've got to do something to make it go around a corner. So it costs no energy for that thing to keep on moving. It's the most. We're so used to tying motion to work. We've got to work to keep our car going because we live in a friction-filled world. So that's why. So we have a bit of a warped view of the universe. And then we talked a little bit about Galileo and inertia, and basically he coined this term inertia, and it is that tendency to keep on doing what you're doing. And heavy objects have more of this tendency. What that means is you've got to affect them more. You've got to push harder to stop a bus from rolling than to stop a shopping cart from rolling. So more mass, more inertia, more tendency to keep on doing what you're doing. And this is about as far as we got. Along came good old Newton, and Newton said, let's codify things. So Galileo was the experimenter, and then Newton did experiments, did a lot of experiments. Newton poked himself in the eye with needles to try and figure out where colours came from. Newton was a very interesting guy. But what he was remarkable for was he was a great codifier. He basically wrote things down, explained things, did math. So that was his particular genius. So in about 1665, about the time of the Black Death in Europe, Newton develops his laws of motion. And the first one, we're going to do three of them at different times, but the first one is the law of inertia. And what he says is, everybody continues in its state of rest or of uniform, that means constant motion, in a straight line, unless acted on by a non-zero, that means non-zero net force. So if you don't push something, if you don't pull on something, then it'll either stay at rest or it will continue at its speed in a straight line forever. And there's various examples we can do of this. We can take a tablecloth and pull it out from underneath a whole bunch of crockery. We can do a simple thing with a card and a coin, and we flip the card and the coin stays put. And we have this other thing where when we have a mass, if we have a piece of string with a mass and another piece of string with a handle, and I pull on the bottom handle, it's not clear whether it will break above the mass or below the mass. I could make an argument and say, well, this has been pulled by that mass and the handle. So yeah, I think it may be going to break here at the top, because there's more force on the one at the top than there is on the one at the bottom. At least when you begin, there's only a handle pulling on this piece of string, but this mass is pulling on that piece of string. But when I pull down quickly, what happens is I find that it's the bottom piece of string that breaks. And what's going on there is the top piece of string will not be pulled until that mass moves, and that mass has inertia. So that mass is reluctant to move downwards. It's the most amazing thing. And you don't notice it in your day-to-day life. You don't kind of like take a shelf down and see all the cans kind of like hanging there in space. But in a way they do. I mean, they don't instantly reach the ground. There's nothing below them, but they don't instantly reach the ground. They take a while to reach the ground. You know, when somebody jumps out of an aeroplane with a parachute, you know, before they open the parachute, they don't instantly hit the ground, but there's nothing there to stop them from falling faster and faster and faster. But it takes them a while to build up their speed, and that tendency is because of inertia. So there is a resistance to speeding up just because of mass in our bodies. So those three are kind of like very nice little demonstrations. And so, I'm sorry, I need to work this out. The pictures are kind of like, so there's a picture of the coin and the feather, and there's a picture of, this is actually at Busch Gardens. I used to do the physics show at Busch Gardens, and so there's the table, and there's the pots and pans on, and these are some graduate students from USF, when I worked at USF, and we got this high school student to come out and pull the thing out, and I don't know if you can see it, but the look of just amazement on her face when she pulled it out, and they stayed there. She did not believe they were going to stay, and she pulled it out, and you can just see that she's absolutely amazing. You know, whenever you're offered a chance to actually do one of these demonstrations, do it, because there's just something about, you do it and you go, my word, it really is true. Okay. So we need to talk about a couple of things. We're going to link force, mass, and acceleration. And so we need to be able to figure out what we mean by a net external force. So what we say is changes in the motion of an object, that's acceleration. Speeding up or slowing down, going round corners, that's acceleration. Are produced by a force or unbalanced combination of forces. Maybe one force by itself, or maybe three forces that don't cancel each other out. When more than a single force acts on an object, we consider this a net force. Net, like net salary. Net salary is what you earn minus your stoppages. It's what you're left with. So that's the net force. Force has both magnitude and a direction, so it is classified as a vector. Vector quantities are added using vector addition. You can't just add the numbers together. You've got to take into account the directions. Now, in three-dimensional space, that's complicated. And in physics, we learn how to do that. But, you know, even on a number line, we just basically take into account the positive and the negatives. It's the same principle, it's just mathematically a bit more straightforward. So vector quantities are added using vector addition, which incorporates both size and direction. So here we have an object and we have two forces acting on it. What's the net force? Well, it's 5 to the right and 3 to the right. They're both reinforcing each other, so that's 8 to the right. We just added, if you like, plus 5 added to plus 3 is plus 8. So now we have a 2 Newton force to the right and a 4 Newton force to the left, so they're fighting each other. So if you like, it's plus 2 added to minus 4 is minus 2. Or if you like, 2 to the right, 4 to the left, that leaves 4 to the left. I mean, you can reason it out, or you can be more formal and do some math type stuff for it. But either way, can you see that these guys are fighting each other, these guys are reinforcing each other? We have to have that skill. And I'm only going to give you it on a number line. I'm not going to go through and give you in complicated space. So that leads us to an equilibrium rule. If you have no net force, so they cancel or there's no forces, or they cancel, then you are in equilibrium. Equilibrium is kind of balanced. Well, yeah, it's kind of like that. You don't change your state of motion. You don't speed up, you don't slow down, you don't go around corners. You just keep on either being still or you keep on going in a straight line at constant speed. It takes a net force to change that. So when you have no net force, so this is the symbol of it, and like all math, it's the fact that you get this shorthand version, and for most people it's like, I don't know what all the symbols mean, and it's a bit hard. But if you know what the symbols mean, it's just like talking. So this means add together all the forces, and it gives you a net force. So you add together all the forces and you get a net force. And when that equals 0, you're in equilibrium, called mechanical equilibrium. Now, something can be in mechanical equilibrium horizontally because the forces cancel. It might not be in equilibrium vertically. Or it might be in equilibrium vertically and not in equilibrium horizontally. So we tend to talk about along a line. Okay, not in any two odd directions. That's the hard thing for my physics, for my general physics people. They kind of like take a force over there and a force over there and they just add them together. You've got to think in terms of a direction. And so you might be in equilibrium horizontally and you might not be vertically. You may be. But if the sum of the forces in any direction add to 0, then we're in equilibrium. So we say we need to practice using clues from the object's motion to recognize when an object is in equilibrium and when it's not. For example, if an object's state of motion changes, its speed changes or its direction changes, are the two clues, it is not in equilibrium. It must be subject to a net force. So we have this pattern, and the pattern goes, okay, if we, let me find my pen here. Do I have a pen? Sorry, let me go here. Is that going to give me, yeah, okay. So let's do it in red. So, let's have a look. If my object is, so if I change my speed, there's one clue. Or, even if I just change direction. I think it's trying to fight me. When not in equilibrium, or both. There's no force, there's no change in speed that cancels out going around a corner. There's no, you can't, I changed my speed, but I went around this special corner, so it doesn't count. If you do either one or both, then you're called, it says you're accelerating. Acceleration is change in velocity in time, and you're changing your velocity because you're changing your direction and or you're changing your speed, and so there must be a net force. So, okay, I could say, look, you changed your direction, there must be a net force. Oh, look, you changed your speed, there must be a net force. Or I could say, hey, you accelerated, there must be a net force. Or you could say, there's a net force, and then you'd say, we accelerated. And I say, okay. And then you'd say, so did we change our speed, or did we change our direction, or did we do both? So either way, you can get it from here or here, but it all goes together. There's an alternative. If the object's state of motion does not change, that means it doesn't speed up or it doesn't change direction, then there cannot be a net force. It's not maybe. If there is a net force, you must do something here. If there is not a net force, you cannot do anything here. And if you do something there must be a net force. If there is nothing done there cannot be a net force. It's like an either or, It's a requirement. So you get used to looking at the motion of an object, and then you can say there is a net force or there's not a net force. Or there must be a change in speed or a change in direction, or there cannot be a change in speed or a change in direction. That's the first thing we got to kind of practice. I'm following the book, so the next thing the book introduces actually is supporting force. And just terminology. This is just like, sometimes you don't realize all the forces that are there. So you put something down on the table and you say to yourself, is that something? Is this box, is it speeding up or slowing down? No, it's not. Is it changing direction? No, it's not. It's at rest. So that means it's in equilibrium. Yeah, it's in equilibrium. So that means if I take a vertical line through it, then there must be no net force. There can't be a net force. Well, there's a weight downwards, let's say 10 newtons. So what must be cancelling out that weight downwards? Oh, there must be a weight up, not a weight, there's force upwards. What should we call it? We're going to call it our supporting force. Now, in physics, again, general physics, we learn to call this normal force. And that's a bit of a misnomer. It's actually normal not meaning the usual. It's normal meaning mathematically at 90 degrees too. Because if I put this on a slope, the force goes with the slope. So the normal force is a bit specialized, but we say we sometimes have to look hard to find all the forces that act on an object. Consider a book on a desk. We know that gravity pulls the book downwards. This is the weight. We know that the book is not accelerating, so it is in equilibrium, and there cannot be a net force. So we have to recognize that the table is pushing the book upwards with exactly the same force, opposite direction, as the gravity is pulling downwards. We call this force exerted by the table the normal force, or the support force. You want to know something a bit frightening, though? Okay. That was 10 newtons, yeah? How many newtons do you think this is? It's like a smidgen of a piece of paper. So now let's think about it. Is this piece of paper accelerating? No. Is it in equilibrium vertically? That means the table must be pushing up with exactly the same force that the paper is pushing down. How on earth does it know? I mean, it's a table. It's not a computer. If I was to do this, if I was to say, hold out your hands, and I'm going to put and I'm going to put something in your hands. So close your eyes. Okay? I'm either going to put this big. I just want to stand next to him because we can see this. I'm going to either put this big, heavy, expensive box in your hand, or I'm going to put this smidgen of paper in your hand. Okay? I'm going to count 3, 2, 1 and put it in. And don't drop it because it's like so expensive. Here we go. 3, 2, 1. Let's do it. 3, 2, no. 3, 2, 1. Okay. 3, 2, 1. 3, 2, 3, 2, 1. Okay, didn't work. I was hoping he'd raise his hand. Because sometimes we're expecting something heavy, you kind of anticipate. And you put too much force in. That's what would happen with this table. If the table anticipated, the table would push too hard. Now, I know what I used to think. I used to think, well, the table's just ignoring the piece of paper. It doesn't even know the piece of paper's there. But from a physics point of view, that's not the way it works. There's a downwards force on that piece of paper. Look, if I throw it over the edge, it falls. It's not been pulled by gravity. It's been pulled by gravity. But it's been supported by an equal force. And if the table pushed up too much, it would go in the air. So the table's pushing with just the right amount. So how does it know? How does it know? Oh, there's a table. Look, close your eyes, table. How does it know? Anybody have any idea how it knows? When you sit on the couch knows. What does the couch do?
Pushes itself down.
Squishes, doesn't it? and it squishes less for small people and more for larger people. So what happens is it kind of gives and gives and gives, and as it gives, it pushes harder. It's like, oh, is that enough? Oh, is that enough? Oh, is that enough? Until it matches, and then it goes, oh, that's enough. That's what the table's doing. If you could get like an atomic resolution viewing machine, you'd see that table sits there like that, and then you put that piece of paper on, and those atoms just move down ever so slightly, but they move. Those things move down until it's in equilibrium. And then when you put this on, it goes, oh man, we've got to move a lot further. Again, you can't see it that well. But if we change the material and put foam rubber there, you can see it. And if I took a piece of wood and I took a steel block, even now we have instruments that could see that. We can see that sort of like deformation. So even a light object. And so that's kind of what physics is about. Physics is kind of getting people to stop making exceptions, you know. To stop saying, oh, I get it for heavy things, but for the light thing, oh, let's just ignore it. Because in principle, it's got to work for the light thing. So there's no exception. There's a rule, a very simple rule, and it applies for everything. And actually, so to that extent, with the exception of the math, physics kind of gets simpler as you go on. Because you see the same patterns over and over again. So until you get to some of the outrageous new stuff. The outrageous new stuff is like so hard to understand. But the classical stuff, it actually gets easier. As if you know gravity, you know electrostatics. It's kind of like, because it's the same simple rules over and over again. So here's a situation. So we have, and I tend to use the same examples over and over again because, to my mind, I don't particularly want you to kind of be scratching your head trying to visualize something you never visualized before. Occasionally, I will throw in a new situation just to see if people are comfortable changing their perspective. But for most times, I'm happy with you if you can visualize what we've been visualizing with the language we've been using, and then can you answer the question on it? I'm very happy about that. So occasionally I'll push a little bit harder. But by and large, I'll kind of stick to these same kind of things. And I like to talk about jet planes, and I like to talk about the thrust force, which is the engine. I don't like to draw forces kind of pushing something. I like to draw forces pulling something. So the thrust force is kind of like pulling the plane forwards, and the drag force is pulling the plane back, and the lift force is lifting the plane up, and the weight is pushing the force leg down. And we say an object can be in equilibrium even if it is moving at very high speed, provided it is moving at a constant speed in a straight line. So consider a jet flying at steady speed. So I just told you that in that direction we're in equilibrium. Because steady speeds means no change in velocity, no change in speed. So that means you're in equilibrium. So I just told you those two forces are equal to each other. In a straight line. A straight line means you're not curving up, you're not curving down, you're not curving to the right, you're not curving to the left. If you're not curving up and down, that means that force is like that force. So can you see how just a few words, and there's a lot of physics implication behind it. The weight is balanced by the lift force, so there's no net force vertically. And the thrust force is balanced by the drag force, so there is no net force horizontally. So there's information in these things. And we'll do some examples of that. The moving Earth. See, here's the problem, and that is that you don't feel speed. You feel acceleration. When you go to the amusement park ride, you're not going for the speed. The speed is kind of exciting, but you can have a very exciting amusement park ride that doesn't go that fast. It used to be that the monorail that takes you from the parking lot to the gate at Disney was faster than any of the rides in Disney. It turns out now, Rock and Roller Coaster Ride, which I guess is in, what's that in, Rock and Roller Coaster?
Was it Epcot?
Is it Epcot? It's one of them, yeah. That's really fast. That uses a linear induction motor to get you going. That's the one where you don't go, it's inside, you don't go up. You just kind of like take off like that. That goes, I think it's like 73 miles an hour. And some of the others, the log plume actually, you know what's the Splash Mountain?
Yeah.
As I never liked rides. When I came to the States, I went on Space Mountain once. I swore the whole way through it. It was like language, and I was like totally embarrassed. I was petrified all the way through it. And then these two 12-year-olds, they got out. That was nothing. I'm just going.
It's a lot slower.
Is it a lot slower now? This was in 1981, so yeah.
The kid died on it.
You know, the dean,
Exactly.
the dean when he was 17 worked on Space Mountain.
Really?
Yeah, he was like one of those guys who were like pressing the
Like an
buttons and all that. So, and then I did rock and roller coaster ride, because my brother-in-law was going to wind me up all day about it, and I thought, I'm not having this. So there's a picture, actually I'll show you next time, there's a picture of me, and my wife, and him and his wife kind of like going like crazy, and my eyes are closed, I am petrified. It's like, I don't like them. As I've got older, so now my daughters, thank heavens, it's kind of like, well, she's a roller coaster demon, she loves them. And but I have high blood pressure, so I told my daughter I can't. Doctor won't allow me to go on the rides. And her best friend's dad's a doctor, so he said to me, with good treatment, you should be fine. And I said to him, and I hope my daughter discovers that in her 3rd year of medical school, because I don't want to do the rides. And but my wife talked me into doing Splash Mountain, and it's that long thing inside.
Yeah.
There were 3 times I nearly got out. I just wanted to go out, and my wife and my daughter just chatting away, and it's loving it, and I can feel the panic rising. And it's like, when we get to the top, I gotta get out, and then we go over the top. And that's not so bad. And then I looked, and that's actually one of the faster rides. That's because it's so high. That's one of the faster rides. It's not speed. It's acceleration. It's going around the corner quickly. It's changing your speed quickly. That's what really gets to us. So one of the arguments that Aristotle made was, he said, look, this is crazy. You say we're going around the sun, we'd feel it. Get in your cart and close your eyes, and you can feel when the horse is moving, you can feel it. And what you're feeling there is that unsteadiness in the motion of the horse. The fact that the horse is not so smooth. But, if you got into a canoe and you just paddled and closed your eyes, could you really tell you were moving? I'm not sure you could tell if you were moving. If you just sat there in a canoe and you just kept it. Well, the canoe's not constant speed, but it's nearly constant speed. So we can't feel speed, but we can feel changes in speed. We can feel changes in direction. That's acceleration. So Aristotle thought the Earth was not moving because he thought that it would take too much force to keep an object as big as the Earth moving. He's going, you're crazy. I mean, look, imagine how many horses you need to pull a cart. How many horses would you need to move the Earth? There can't be that amount of energy in the entire world. So he didn't realize that once it's moving, it keeps moving. Yeah? Once it's moving, it keeps moving. Getting the Earth starting to spin took a lot of energy, but once it's moving, it keeps moving. He observed that the Earth doesn't move sideways when you toss an object out of contact. So if I take a pencil and I'm on a cart and I throw that pencil up in the Earth, especially if there's air resistance, it tends to blow behind me. If you take a piece of paper, if you have anybody got an open top car? No, not so. If you have an open top car and you throw a piece of paper up, it'll be behind you. Yeah. If you take a piece of paper in a closed car and you throw it up, it doesn't go into the back seat. It's the air that's blowing it into the back seat. But he wasn't. They didn't have closed vehicles, I guess, 3,000 years ago. So basically, his argument was, if you throw something in the air when you're moving, it will be left behind, and it's never left behind. So you can't be moving. Not really true. And then Both arguments are wrong. A force is not needed to keep the Earth moving. An object that is thrown out of contact with the Earth was originally travelling at the same speed as the Earth, and so its inertia keeps it moving at the same speed. In addition, the atmosphere is also moving at the same speed. So basically, you know, you're all going at 500 miles an hour. You keep going at 500 miles an hour whether you're touching the apple or not. By the way, how fast are we travelling around the centre of the Earth? Anybody got an idea? We're travelling at about 1,000 miles an hour. This room is going at 1,000, twice the speed of a transatlantic jet.
Is that
Just because it's spinning.
just the spin? What about like, yeah, when you put it up?
Something like 93,000 miles an hour around the centre of the galaxy, around the centre of the solar system. And then I think it's like something like over 500,000 miles an hour relative to the galaxy. Those numbers coming up in a while. Do we do this? Did I do the clickers with you before? Do you want to do them again?
Yeah.
Yeah, let's do them. Okay. So let's look. 1, 2, 3, 4, 5. The actual the numbers don't matter. It's all anonymous. It's just so that it slows me down a bit, and it kind of lets you know. We need one more. Sorry. It lets you know whether or not you get put the same answers down as everybody else. And then let me get my wireless set up. It won't take me long. Eventually, I'll be organised enough that I like the college to actually just put this stuff in here so it's permanent. That'd be great. So we have our little radio thing that your machines talk to, and then I plug that in there, and then I plug it in there. Now that don't work. Plug it in there. And then this needs power, I guess. So it looks like it's got a battery inside it, but we'll just keep it plugged in just to be on the safe side. And then I have to just close this window for a second, and then I go here to my clicker, which is there, and then I go to iClicker, which is there. And then, let's have a look. AB, is this you guys? No. AB, why on earth am I doing this? It doesn't matter. Test, I'll do this. New session, resume, start session. It's going to think for a minute. Maybe I should double click. It's going to think for a minute. There, question list available. No. So then I come along here and I go, let's have a graph. There's my graph. And then what I'm going to do is I'm going to put you down to the bottom, and then I'm going to open you up again. This might be interesting. Open you up again. So here we go. So put this over to that side. Actually, I don't want you to see this yet. So what I'm going to do is I'm going to do this. I'm going to I don't really want to close it. I want to just hide it. So put you to the bottom, and then put you on top. Will you come up on top? No? Okay. We'll figure it out. That's something I need to... Okay. So let's look. A car is travelling at a steady 60 miles per hour along a straight and level road. Is the car in equilibrium along the horizontal axis? A is yes, B is no, C is need more information. So start clicking away. We've got about 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, about 18 people. So we'll 15 or 16 people will be fine. That's great. Okay, any more want to go? So let's have a look. There's 17. Let's go. So most people are saying A, and a couple of people are saying B. So let's look at this. So A would be yes. The car is traveling at steady 60 miles an hour. That means not speeding up, not slowing down. And it's along a straight and level road, so it's not curving around any corners. So that means it's in equilibrium. If you don't speed up and you don't slow down and you don't go around any corners, you're in equilibrium. So the answer to that one is A, yes. Is the car in equilibrium along the vertical axis? What do you think? Along the vertical axis? And we got 16 votes. 17, 18, good. 19, good. 20, okay. Oh, that's the time. That's amazing. Let's look at the graph. Let's stop it and then look at the graph. So, a bit more selection here. So most people said A, some people said B, some people said C. So then let's go through this. So let's have a look. A car is traveling steady 60 miles an hour along a straight and level road. It's level. It doesn't curve up, it doesn't curve down. And from a vertical point of view, you're not climbing up or climbing down, you're just going horizontally. So you've got no speed vertically, it's not changing, you're not getting a speed vertically, you're not losing a speed vertically, so there's no change in speed vertically. And the road doesn't go vertically up or vertically down. It doesn't curve at all, it's a straight and level road. So again, equilibrium vertically. So the answer's A on that one. The answer's still A. A car is steadily accelerating from rest. Let's start this one. A car is steadily accelerating from rest to 260 miles an hour along a straight and level road. And the question is the car in equilibrium along the horizontal axis? So we've got 18, that's good enough for me, that's for sure. So let's have a look at what our graph says. And most people are saying B, which is no. A couple of people are saying yes, A, which is yes. So let's justify this thing. So you're accelerating because you're changing your speed in the horizontal direction. And once you're accelerating, it means you're no longer in equilibrium. So the answer is no, you're not in equilibrium in the horizontal axis. So the answer is B. Now, is the car in equilibrium along the vertical axis? Let's try that one. I've got to click you in. Okay. So now think vertically. Going at a steadily accelerating, steadily changing your speed horizontally on a straight and level road. Straight and level road. So think vertically now. Think vertically. Ask yourself, is my vertical speed changing? Or is my vertical direction changing? Yeah, we got just one more second. Come on, number 18. Come on. Okay. Let's have a look. So it says most people are saying yes, I am in equilibrium in the vertical axis, but more people, 5 people, are saying no vertically. Well, the answer is A. The answer is yes, you're in equilibrium. So what's going on here? You are changing your speed, but you're changing your speed horizontally. You're not changing your speed vertically. You're not climbing the hill, you're not descending. There's no speed vertically. So you're not changing your vertical speed, and you're not changing your vertical direction. You're not curving up or curving down. So you can be in equilibrium horizontally and not vertically, or in equilibrium vertically and not horizontally. So get used to passing that out. Good. And then also let's stop this. And then, is that the end of it? Or is that, have a look. So now, yep, that's the end of that. Okay. So am I doing for time? Okay, a little bit more. Okay. So let's stop there. I have put the answer key to the homework online. Why? Because it's like 42 questions long, and to go through that in class would take a while. But the answers are not sometimes straightforward. So I want to do this. I want you to go through the homework. I'd like you to do it if you've not done it. I'd like you to do it. I'd like you to check your answers. I'd like you to see where you don't see why I'm getting what I'm getting. And then next time we'll focus on those, I didn't get answer. And the deal we got to have is that you got to just not be embarrassed. If believe me, I've taught this class lots of times. If you're not getting something, other people are not getting it too. It's not only you that will not get something. So you got to be a spokesperson and say, we got a new president, and he was giving a presentation. This was years ago. He was giving a presentation to the faculty. His first day on the job, brand new president, and he said, "Are there any questions?" And nobody wanted to ask a question. So I thought, no one's going to ask a question. Someone's got to break the ice. So a bit kind of wickedly, I said, I like wearing ties. And HCC does not have a college tie. Will you organise a college tie so that when people graduate, they can wear a college tie? When they're in business, they can wear a college tie. And I thought it's a real nice softball question. And he was not expecting it. And he said, "Man, I'm the last person you want to have a college tie. Why would you ask me to get you a college tie?" So, and the people around, I could see this guy next to me just rolled his eyes, And then people asked serious questions. So I did my social bit of asking a softball question. It would have been nice if he'd said, "That's the best idea I've ever heard. What's your name?" I've actually thought about, you can go online and have ties made. I've actually thought about going online and having a HCC tie made and then giving him one. So, there's money to be made in that. There's money to be made in that. You think graduation, your parents are there. They want you to look nice. They're gonna, if there was so most places have a college tie with the name on, or they have like a pin, or they have like a scarf or something for women. It's like there's money to be made in it. We've got 42,000 people in this college. That's a lot of ties, even if they only wear it once a year. That's a lot of ties. Okay. But I'm not going to do it. Okay. So the next one, linear motion. So let's talk a little bit about linear motion. That's all recorded, Dad. And he's a very nice man too, that's going to say, because I'm recording all this. So let me make sure that I don't get into trouble. So 100% I can do it, yeah, okay. So linear motion. We want to do, in this next bit, we want to keep track of things moving, along a line. And we've got to learn some new terminology. So we have what's called speed, we have velocity, we have position, we have displacement, we have pickup, we have acceleration. Oh. I've got a new version of this, which is a little bit better, but this is fine. It's got the same material, it's a bit, I put a bit more detail in the new version of it. Where did I get this from? I got this from my notes, isn't it? These notes are not right. Okay. So I'm going to end you